Kepler's three laws describe the motions of the planets, but they don't explain them. Isaac Newton's explanation of those laws was the culmination of the scientific revolution. It's known as the solution to the Kepler problem.
Let me remind you again briefly of the story we've heard so many times. In 1543, Copernicus wrote his little book. A generation later, Kepler discovered his three laws. And then, 150 years after Copernicus, Isaac Newton came along and explained for us why the universe works the way it does. Today, we're going to begin the job of seeing exactly how Newton's laws explain everything that Kepler found in the heavens. Now that sounds hard, and it is, but it's one of the crowning achievements of Western thought. It's a part of your cultural heritage in the same sense as Shakespeare's plays, or Beethoven's symphonies, or the ceiling of the Sistine Chapel. And so I'd like you to learn this, not merely as a part of your vocational training for those of you who are going to be scientists, but as a part of your education as human beings. Now, what we're going to learn today differs from a play or a symphony or a painting in a fundamental way. A painting, for example, is the creation of a single person. If anyone else had painted the ceiling of the Sistine Chapel, it would have come out completely differently. But what we're going to learn today is a fact about the physical universe. If it had not been discovered by Newton, it would have been discovered by somebody else. And so there's no need for us to do it in exactly the same way that Newton did. We can use tricks that came along later, like vectors and energy, things that will make the word simpler. And that's what we'll do. But once it's done, then unlike a painting, it's something that will belong to you every bit as much as it originally belonged to Newton. It will be your very own to take with you forever. This is the job we've been preparing for ever since we started. And now it's time to get going.
Isaac Newton guessed that the force of gravity gives rise to elliptical orbits. And he found the proof for that guess in worldly mathematics. Into Newton's mathematics went his inverse square law of gravity, as well as his second law of motion. And out came a differential equation for the orbit, whose solution is the algebraic equation, not only of an ellipse, but of any conic section. And that vision, Isaac Newton's enormous leap of insight, rose to stand among the greatest achievements of Western culture. It was, in its own right, the mathematical equivalent of Michelangelo's ceiling in the Sistine Chapel, the crowning glory of the Renaissance. Michelangelo's subjects seemed to be in constant movement, never at rest. And by virtue of this perspective, Michelangelo, like Copernicus, seems to glorify the never-ending motions of the earth and all its creatures. With such a brilliant perception, both the scientist and the artist shared the uncommon worldview of the greatest playwright in history. In creating his extraordinary world, where did William Shakespeare place the sun?
But soft, what light through yonder window breaks? It is the east, and Juliet is the sun. Arise, fair sun, and kill the envious moon.
Shakespeare lived in the days of Galileo and Kepler. And just as surely as they did, he worked under the influence of the heavens and often used celestial references.
Her eye discourses, I will answer it. I am too bold. 'Tis not to me she speaks. Two of the fairest stars in all the heaven, having some business, do entreat her eyes to twinkle in their spheres till they return. What if her eyes were there, they in her head? The brightness of her cheek would shame those stars, as daylight doth a lamp. Her eye in heaven would...
Of course, Shakespeare wasn't the only creative genius to make a powerful connection between the arts and the sciences. Finding his inspiration to compose Ode to Joy in the Stars, Ludwig van Beethoven sang the praises of the heavenly firmament. Fine art, drama, music, mathematics and physics. Each is a brilliant gem of Western culture. And collectively, they are the crown jewels of Western achievement. Even as a young man, Newton realized that gravity was the common force of heaven and earth. He saw it as a fundamental force that consistently pulls rather than pushes or twists through the universe. Years later, with that in mind, Isaac Newton fully appreciated the meaning of Kepler's laws of planetary motion.
Twist or torque cannot be applied by gravity. Zero torque, together with Newton's second law, leads to a differential equation ready to be integrated. When there is no torque, a certain quantity, mr cross v, is constant. That quantity is called the angular momentum. A planet orbiting with constant angular momentum stays in a single plane. Its orbital speed varies in a precisely determined way. The area swept out by its radius vector changes at a constant rate. That's Kepler's second law.
When Johannes Kepler rolled toward his second law, the art of astrology and the science of astronomy were one and the same. And whichever it was called, the terms were interchangeable then, Kepler, like the typical mathematician of his day, used it as a means of producing income. But unlike the others, Kepler used astronomy as a vehicle to reach a mathematical truth that had been hidden within the heavens since the day of creation. At the same time, with his poetic interpretation of astronomy, Shakespeare searched for a universal equation that could explain the complex actions and complicated emotions of women and men. And like Isaac Newton, his observations influenced the way humans perceive reality. Their methods differ. Newton was hardly known for his sense of humor.
Yes, indeed, sir. I have spoken to him. I'll go and see him again.
But like Shakespeare, Newton asked questions that deeply affected perception of how the world works. Newton's discovery that the orbits of all objects in the heavens Obey the equation of the conic sections started out as a question. Why are the planetary orbits ellipses, sweeping out equal areas in equal times?
The answer is most easily found in polar coordinates, where the rate of change of area is equal to 1/2 r squared d theta dt. In terms of angular momentum, the result is a differential equation obeyed by all objects moving under any central force,
including planets moving in elliptical orbits under the force of Newton's universal law of gravity.
The heavens themselves, the planets, and this center observe degree, priority, and place. Insist your course, proportion...
In Shakespeare's time, the Earth, influenced by disordered and wandering planets, was at the core of the solar system. Yet in Troilus and Cressida, did he not place Sol, the sun, at the center of his drama?
Is the glorious planet Sol, in noble eminence enthroned and sphered amidst the other, whose medicinable eye corrects the ill aspects of planets' evil and posts like the commandment of a king.
Was William Shakespeare, in fact, a Copernican? Did he share the same worldview as Johannes Kepler? Like a tragic character of Elizabethan drama, Kepler traveled a path of cruel and ironic twists, seeing perfect harmony in the heavens, while experiencing total discord on Earth. As a young boy, Kepler was abandoned by his father, a brutal mercenary who drifted from war to war. Young Kepler was shipped off to a Protestant seminary in the German provinces. It was a strict and Spartan life, with endless hours of study and prayer. Kepler was a frail and sickly lad who had virtually no friends and was stubbornly independent. Kepler's mother was an eccentric in the extreme, obsessed with astrology and the occult. His aunt was burned at the stake. As his religious training progressed, he despaired about ever being saved and became increasingly guilty about his mother's fascination with the occult. Later, as for his own family, he lost his first wife and 7 of his 11 children. A wandering victim of the 30 Years' War, he carried his pain from city to city, seeking a port in the violent storm that followed him the last 12 years of his life. Of course, things could have been worse, and they soon were. In 1615, Kepler's mother was put on trial for the fairly common but forbidden practice of witchcraft. Devastated by the news of his mother's arrest and trial, Kepler wrote, "It caused my heart to almost burst." Though he was finally making real progress in his life's work, he stood by his mother in one way or another for 6 long years. Because Kepler himself described her as a stubborn and quarrelsome gossip, Kepler's heartfelt concern for his mother seems a curious footnote. Other than a dutiful son's strength of character, was there another reason to owe the old woman so very much? In the story of his childhood, which is a dark chronicle of misery, Kepler wrote of only one bright moment. When he was 5 years old, curious and very impressionable, His mother took his hand, and they strolled out into the night. They climbed to the top of a nearby hill, and together they saw a comet. While the reason behind his accomplishments must trail off in speculation, the accomplishments themselves remain indelible. While William Shakespeare probably would have overlooked the mathematics that reflect Kepler's third law, surely he would have found irony in the title of Kepler's work, The Harmony of the World. Despite his mother's ordeal, his loss of one child after another, his ongoing conflict between scientific fact and religious dogma, nothing could keep Johannes Kepler from completing the harmony of the world. And yet, even though his mind was able to cross the most advanced frontiers of the world of mathematics, Kepler himself never fully realized the extent of its reach. On the final leg of his wandering, he almost came across the calculus, but that would be reached by Leibniz and Newton. By the same token, Kepler came close to the universal law of gravity, but that would be the destiny of Isaac Newton alone. Not only did it fall upon him to discover the universal law of gravitation, the law itself fell into Newton's hands as the key to the Kepler problem. With his law of gravity, Isaac Newton unlocked the door Kepler had approached for a lifetime and stepped across the threshold into the secret of the skies. The universal law of gravitation. The second law of motion. The conservation of angular momentum. Vectors cross together like Shakespeare's star-crossed lovers. In a combination as potent as Michelangelo's Hand of God. Setting off a ballet of vectors as spirited as a Beethoven symphony. The equations of the heavens find their simplest expression in the elegant language of differential calculus. Integral to the grand design and constant in addition. The ellipses of the heavens are revealed as an expression of the perfect circle of underlying geometry. The product of these events, once order is exchanged, and mass
allowed its play, comes to resemble an old friend, a curve of familiar aspect. Ellipse, parabola, and hyperbola all find their arcs described on the celestial tapestry.
And so, as Isaac Newton was the first to discover, the force of gravity moves all heavenly bodies along conic sections. And since planets move in closed curves, their orbits are ellipses. Newton casually shared this discovery with Edmund Halley. But Halley's reaction may have soon changed from pure joy to absolute horror. Not only had Newton lost his calculations for solving the Kepler problem, but he'd even forgotten how he had derived the mathematical proof. However, urged on by Halley, Newton calmly started once again to solve perhaps the most complex problem in the scientific world. And this time, he went on to reveal the mathematical secret of the universe. Considering such beautiful lines, Shakespeare's dialogue, Beethoven's phrasing, Michelangelo's brushstrokes, and the strokes of genius in Newton and Kepler, it becomes increasingly clear that the greatest art and science endure not only for their elegance, but for their truth.
Johannes Kepler lived at the same time as William Shakespeare, Queen Elizabeth I, Mary Queen of Scots, and of course, Galileo. So far as I know, no two of those people ever met each other. But Kepler and Galileo certainly knew about each other, and in fact, they even exchanged a few letters. I'd like to read to you a little bit from those letters. The first one is written in 1597. Kepler had a copy of a book he had written sent to Galileo, and Galileo sent back his reply. He wrote, "Your book, my learned doctor, I received merely a few hours ago. I congratulate myself on having an associate in the study of truth. And truth, spelt with a capital T, meant to Galileo the Copernican system of the world. He had not yet admitted openly that he believed in it. In fact, later on in the letter he writes, so far, I have been frightened by the fate of Copernicus himself, our teacher, who, though he acquired immortal fame with some, is yet to an infinite multitude of others, for such is the number of fools, an object of ridicule and derision." You remember that 40 years later, Galileo himself was put on trial for adopting the Copernican system. The second letter was written in 1610. Galileo had made his brilliant discoveries with the new telescope, written a book called The Starry Messenger, but the book was received with either indifference or hostility by the rest of the world. He had a copy sent to the great Kepler and waited with anxiety for his reply. Kepler replied with his characteristic generosity, and Galileo then wrote back to him, "I thank you because you are the first and nearly the only one who has shown complete faith in my assertions. Not at all surprising, such is your nobility and the height of your genius." Kepler asked Galileo how he could get to see the heavens through a telescope of the quality of the one that Galileo had made. Galileo wrote back saying there was none available to him either. He wrote, "Indeed, mine is truly excellent, and it multiplies images more than 1,000 times. It is no longer mine. The most serene Grand Duke of Tuscany sought it from me so that he might store it in his tribunal, and there, among more distinguished and costly things, preserve it in lasting memory." Every scientist today is familiar with the risks and hazards of working under government patronage. Kepler did personally meet Tycho Brahe, and that meeting changed the history of the world. These were bad times. In 1597, Tycho's patron, King Frederick, died, and he was succeeded by Christian IV, who couldn't stand the arrogant astronomer. And soon Tycho had to leave Denmark. He wound up in Prague as imperial mathematician to Rudolf II, where his job, of course, was to cast horoscopes. Meanwhile, back in Austria, Kepler, who was born a Protestant, was hounded out of the Catholic town of Graz. And so, on a date that's very easy to remember, the 1st of January 1600, he set out to join the great Tycho in Prague. And that's how the two of them met. Immediately, they both realized that they couldn't stand each other, but neither one could get along without the other. Tycho needed Kepler's mathematical genius to organize his observations, and Kepler had to have Tycho's data to do the cosmology, which was his life's mission. And so, for 18 stormy months, the two of them stayed tied together, unable to escape from each other, until Tycho died in 1601. And even then, Kepler was not able to turn all of his attention to the cosmology that he so badly wanted to do, because first he had the responsibility to produce this book. This book is called The Rudolphine Tables, after the Emperor Rudolph, who paid the bill. It's written by Johannes Kepler, published in 1627, and it is Kepler's publication of Tycho's data. Even if Kepler had never discovered his three laws, we would remember him today for this book, because this book made astronomy 100 times more precise than it had ever been before. We'll go on with our story next time.
Annenberg Media. For information about this and other Annenberg Media programs, call 1-800-LEARNER and visit us at www.learner.org.